Okay, welcome. This is New England Dynamics and Number Theory seminar. Today's speaker is Vasiliy Neckrasov from Brandeis, who will talk about 0-1 laws for uniform inhomogeneous Diophantine approximations. I hope you'll explain all these strange words to us.
Of course, yeah. Thank you, Dmitry, for introducing me and for actually giving an opportunity to speak on this seminar. So today I will speak about my recent work. It will be based on two papers that I uploaded on arXiv this year, my paper and my paper with Nikolai Mashevitin. But these papers focus on twisted and homogeneous approximation, both uniform and asymptotic. This time I will just talk about the uniform part, so I will leave the asymptotic part for maybe for another talk. I partially explain some results of it on another seminar. Maybe I will do it once again. I want to start slowly with setup and a lot of notation, so probably the first part of talk will be rather boring, especially to the specialists, but I know that there are many people who are not specialists, and I will try to make things clear and start slowly. Then we will see the main results, and then if time allows, I will try to show some rather simple but non-trivial proof to show how this all is done. Okay, so let's start with the notation and conventions that will be used throughout this talk. First of all, we always denote the dimensions as M and N, dimensions of matrices. M and M is a set of N by M real matrices. Matrices will always be called theta, and the entries of matrices will be called theta sub ij. And eta will always be an n-dimensional real vector. I will refer to it as a shift vector. Pretty often I will refer to it as a shift vector, but generally it's just an n-dimensional vector. Finally, this is a notation for supremum norm. I will not write infinity or max or something, just one vertical line is a supremum norm. And two vertical lines, sometimes I will use the subscript z and sometimes not, but two vertical lines will always refer to the distance to the nearest integer function. The distance to the nearest integer is a function where we take the minimal norm of all the integer shifts of our vector. So we consider the minimum over all the shifts by an integer vector, and one vertical line becomes 2. So what are we talking about first in general? The very general setup of inhomogeneous Diophantine approximation. The classical homogeneous Diophantine approximation studies the, sometimes people call it systems of linear forms. We can call it one vector form, theta q, and people study how small the distance to the nearest integer of this form is under some restrictions on the vector, on the integer vectors q. We will talk about the more particular restrictions later. So this is the more classical and very well studied setup. In homogeneous setup, we just replace this linear form with an affine form. So we shift this value by some vector eta. This vector can be fixed. This vector can be not fixed. Again, we will see different examples later. And we ask the same question. We ask the question how small it can be with certain restrictions on q, and the notion of what it means to be small and what the restrictions on q can be can vary. We will see again the possible examples. So more precisely, inhomogeneous Diophantine approximation studies this system of inequalities. We have well, at least the easiest setup in the classical norms. So we have some restriction for the norm of this vector q, and under these restrictions we want to compare the distance to the nearest integer of this affine form with some fixed function g of this variable t. So t is just some parameter, and we care about solvability in integer vectors of this system. Now there are at least two natural questions that one can ask for solvability of the system. First question is, can this system be solved for any t no matter which parameter t we take, this system will have a solution. Or maybe we can weaken it a little bit and say for all t at least large enough. At least eventually, no matter which t we take, we can do this. This is a setup that's usually referred to as uniform approximation. This system of inequalities uniformly has solutions for all large enough t. We will denote the set of pairs theta eta, which have solutions for all t large enough. We will call them Dirichlet, and we will denote this set of Dirichlet pairs as d of a function g with a hat. So the hat will be used, this is also a convention that will be used throughout the whole presentation. The hat will be used for the sets in homogeneous approximations, which will be the sets of pairs or some sections of the sets of pairs, versus the notation d and later w without hats will be used for homogeneous approximation when we just have matrix and no shift. And the other setup is the setup of asymptotic approximation. We have a more relaxed restriction. Instead of demanding that this system of inequalities has solutions for all t large enough, we just require an unbounded set of these solutions. Well, you can think of it as infinitely many integer t which work. In this case, we call the set G approximable and denoted by the letter W. So more specifically, probably here it is more clearly formulated. First, if we require solutions for any t large enough, it is called G Dirichlet and denoted as D. And second case, if we require G approximable, we require this system to have infinitely many unbounded set of solutions. And we denote this set as W nm of G. And it is well known that the solvability of this one inequality for infinitely many Q is equivalent to solvability of this system for infinitely many T. Okay, now we want to generalize this classical setup. This was all in the classical supremum norm. We want to generalize this classical setup a little bit by, in a way, changing the norm. But when we change the norm, it pretty often stops being a norm. So I will sometimes refer to it as a norm because it's simpler, but I will specify that it's not really a norm. It's just some analog specifically for our case. So we want to consider tuples of functions, which we denote alpha and beta. With some restrictions, they are increasing, they are continuous. They have a technical condition that their values at 1 is 1, but it's, again, pretty technical. And what is probably the only real important condition is that these functions, let's say we can define them for the interval from 1 to plus infinity, and then we can use convolution to define them for small values of t. This is presented on the picture. So in some sense, we have independent almost without any restriction parts from 1 to infinity, and the part for the smaller t is fixed after we fix the part for bigger t. So what do we do with these weight functions, and why are they called weight functions? We are considering the corresponding analogs of norms, the corresponding ways to measure how long, how big the vectors are. Specifically, this is the definition, and we are taking the maximum of alpha inverse of coordinates of the vector, or of beta inverse of coordinates of the vector, depending on the dimension. And we will denote this notion of analog of norm by subscripts alpha and beta. We can define analogous with the distance to the nearest integer with respect to alpha and beta. Now, probably after introducing this rather general setup, I need to comment on why this is natural. So it is natural, at least it is natural in a sense that our classical case with supremum norms can be obtained as a special case here. For this, we just take all the alpha sub I and beta sub j to be the function t itself, and it's easy to see that this gives the definition of supremum norm. This example probably does not explain one thing. It does not explain why we take alphas and betas inverse. And the reason for taking alphas and betas inverse is because we want to match the also already becoming classical setup of approximations with weights. I will talk about it a little bit later. I first want to introduce the approximations with general weighted functions, and then approximations with weights. What people usually mean by approximation with weights will be one of the special cases. So the definitions are basically the same. We just replace supremum norms by norms with respect to weight functions alpha and beta, and analogously define the set of approximable and uniform to have different examples of definitions. I give first definition here for the matrix theta transposed, because we will be using it mostly for theta transposed, and just for the set of matrices, so this set does not have hat under above it. Okay, so this is what goes to the, well, you can notice that there are some modifications in terms that in our previous definitions we took the powers of these supremum norms. Here we do not. It will be probably clear why we are doing it this way right after we see the example of approximations with weights. These definitions are analogous, as I said, to the classical ones, but it's not very convenient to work with this notation, the distance function generated by alpha and generated by beta. So this is an explicit form of what exactly the inequalities we're looking at are. So we want to bound each coordinate of, let's say, for example, here, integer vector y separately, and we want to bound each distance to the nearest integer for each row, for each separate affine form or linear form separately, but it's not completely independent. So it's not the case when we just have different functions f1, f2, fm. We still have we have different fixed functions beta of this one and only function. So it may seem that we have more degrees of freedom than necessary here, but for most of our statement, for the transference principle, for applications of transference, this is actually the most natural setup for this problem. And probably I'll talk about it shortly because it's not too important for us right now. To work with these functions, of course, we can define all these notions for arbitrary functions, function tuples alpha and beta. But for these sets to have natural properties, to have interesting properties to satisfy our theorems, we still need some restrictions on these functions alpha and beta. In particular, what we will require from now on, starting from this slide, for the functions which will be called alpha and beta throughout the text, is a property of quasi-multiplicativity. Quasi-multiplicativity, here is the definition, but what it really means informally is that on long distances, our function is bounded from below and from above by some polynomials. It has not faster and not slower than polynomial growth. We still can allow this function to behave arbitrarily on some short intervals, but long time, so here the polynomials will be actually t to the power logarithm of c1 and t to the power logarithm of c2. So it cannot increase too fast and it cannot decrease too fast, at least for a long time. Here are some properties of quasi-multiplicative functions, which I will not list, but they are pretty natural. Quasi-multiplicativity holds under many function operations, some product composition, and so on and so on. And another clear and important property is that we can check quasi-multiplicativity on the functions which are extended by this convolution, just for big enough or just for small enough close to zero values of the argument. Again, as I said, it's a rather technical condition, so I don't want to discuss it for longer, but it will be used and it will be assumed everywhere that alpha and beta satisfy this technical condition. Finally, the examples. Finally, the approximations with weights that I promised. So instead of, this is also a well-studied subject in Diophantine approximation, instead of the supremum norms, we take quasi-norms. Finally, I can use these words because these are indeed quasi-norms, defined by weight vectors rho and sigma. Here are the definitions, and instead of just maximal of absolute values of coordinates, we take these coordinates to the powers 1 over rho I and 1 over sigma j. And there is normalization, which makes sense to make for rhos, not for 1 over rhos, and for sigmas, not 1 over sigmas. Again, there are many reasons and many explanations why this normalization is natural. For example, the dynamical explanation that we want to preserve the volume. But for this reason or for another reason, they are pretty natural. And in this case, it corresponds to our weight functions, where we take alpha i's and beta j's to be powers, corresponding powers of variable t. These are, yeah, and we will also use, we will abuse the notation slightly. So you may remember that the notation for general weight functions was the same with rho and sigma replaced by alpha and beta. So we used to think of alpha, betas and as functions. Specifically, when we use the letters rho and sigma, we think of these as the weight vectors instead. Again, this convention will be, we will hold to it for the whole talk, so I hope it will not generate any problems. But these are, of course, rather trivial, in a proper way of saying this, examples of quasi-multiplicative functions. It's very clear that these functions are quasi-multiplicative because they are themselves the powers of t. Of course, we can modify them slightly, add logarithmic factor or double logarithmic factor, take sum of different terms and do all of that, but this is not a big difference in sense of what we are really studying. Maybe a bigger difference can be shown, I will show it on a special case, on this next slide. So let us, for a moment, instead of general metric theta, just for simplicity, consider an affine form, one affine form of two variables, theta 1 q1 plus theta 2 q2 minus sum shift eta. And let's also, for simplicity, say that the function alpha of t is just equal to t itself. So we are just approximation by the function g. But we want to measure q1 and q2 with respect to some weight function beta 1 and beta 2. So if we were in the classical approximation with weights situation, we would have t to the power something and t to the power 1 minus something. For example, t to the power 1/3 and t to the power 2/3. And we can fix the weights and study the system. Then we can fix some different vector of weights and study separately another system. So the question is, can we find such functions beta 1 and beta 2 that for some t, this setup will correspond to approximations with weights 1/3 and 2/3, and for some other t, it will correspond to approximations with weights which are, let's say, shown in the other order, 2/3 and 1/3. So can we switch between these two weights infinitely many times? It turns out that this example is rather easy to construct. These functions beta 1 and beta 2 are rather easy to construct, which satisfy these properties. Infinitely many times, first function is power 1/3 and second is power 2/3, and then they alternate and then they alternate again. So we are at once, for different times, considering two different setups of weighted approximation. This function is easy to construct as a piecewise linear function on logarithmic scale. So logarithmic scale is very convenient because basically for classical, again, setup of approximations with weights on logarithmic scale, our functions are just straight lines with different slopes, where slopes are exactly the weights. And it is clear that we can alternate between these two linear functions using piecewise linear functions also with bounded slopes. And boundedness of slopes is the condition that gives us quasi-multiplicativity, which in turn will be used for all of our proofs. So if you are considering the function that's e to the power of these blue and orange functions, you can apply all the theorems that I will talk about in this presentation. Another comment that also I will not talk about this in the presentation. This is a topic for another discussion. But you can look at Diophantine approximation from the dynamical point of view. You can consider the trajectories on the space of lattices, and you are considering basically the action of some diagonal matrices to some lattices, and see how the trajectories act. So classically, on logarithmic scale, what you are applying are the straight lines. And instead of this, with our new theorems, you can say something about the situation when you apply some curves with some restrictions, which are follow from quasi-multiplicativity. They can be reformulated in terms of action of the matrices. It will not be a subgroup anymore, but we can say something about trajectories under the action of some curves. Okay, finally, finishing the setup section, we will not just consider the sets of pairs theta and eta, but we will also consider the sets where we fix one of them. So unlike the homogeneous approximation where we just care about matrices, here we can just from the start have three different setups. One setup is when we are considering the set of pairs, and two other setups is when we fix a matrix and consider the set of vectors eta, or we fix a shift vector eta and consider the set of corresponding matrices. So there are three possible different setups, and they should be studied to some extent separately, although of course there are relations and we will see them today as well. So today I will focus on the ones that are painted blue. I will not talk about the approximations with fixed shift vector. There's a lot known about these sets with the shift vector. For example, the whole metric theory of sets with the shift vector being fixed. Well, not for weight functions, but for usual norms is known. You can you know precisely all the Hausdorff dimensions of these sets, and it's a work of Tae-Hong Kim, who is here today, and it was actually generalized this year to the approximations with weights, not with arbitrary weight functions, but with classical weights. Yeah, I will also not talk about the asymptotic approximation. I will not talk about the sets W. They will only show up for homogeneous case, because we will use the transference between homogeneous and inhomogeneous situation. So we will only talk about Lebesgue measures of the sets D hat and D hat with a fixed matrix theta. Okay, so finally, I can start talking about the results. I hope I covered all the notation so that we can get back there if necessary, but generally not stop and discuss more and more new symbols. So I will start, as soon as this is a talk about Diophantine approximation, I will start with Dirichlet theorem. First of all, it's just a good tradition, and second, it's a good opportunity to see how the classical theorem looks like in this notation. So classical Dirichlet theorem, yeah, we will introduce also the notation f sub a is 1 over t to the power a. And in this notation, classical Dirichlet theorem just says that every matrix is F1 Dirichlet. That's all that the theorem says. So Dirichlet theorem just gives the bound for all the matrices. Now, can we do something with weights? It turns out that, well, it's rather clear that yes. I don't know if someone has done it before or not, but it's a two-line proof. You just look at the lattice geometry and see it more or less immediately. That the analog of the Dirichlet theorem can be stated in terms of arbitrary weight functions. Just instead of the function f1, we need some function that I denoted by G alpha beta here, which is defined via alpha and beta. And you can, as a sanity check, you can see that if alpha is equal to alpha of t is equal to t and beta of t is equal to t, this function is exactly 1 over t, so exactly the function from Dirichlet theorem. So this is a rather simple observation that for this setup, analog of Dirichlet theorem also holds. This allows us to just use it as a starting point for studying this setup. But, okay, Dirichlet theorem gives us some statement that holds for all matrices. The next natural question is, can it be improved? Can it be improved for all matrices? The answer is, of course, no. And can it be improved for some matrices? The answer is, of course, yes. How big is the set of matrices for which it can be improved? For the classical Diophantine approximation, this question was answered. It's a Davenport-Schmidt theorem. And it says that if we, instead of our function f1, multiply it by some constant strictly smaller than 1, no matter how close to 1 it is, we immediately get a set of zero Lebesgue measure. So Dirichlet theorem is optimal for almost all matrices for the homogeneous set. I did not find, to be honest, a reference to the theorem with weight. I don't think someone, I'm not sure that it's explicitly stated in the literature, although it's clear that the same result should hold. And I'm not sure that it's written in general weight functions either. But I guess it's not that important in this case because there is no real difference in this situation. Now the question is, let's start with the twisted Diophantine approximation, so-called twisted approximation. Yeah, I didn't introduce this language. By twisted Diophantine approximation, I will mean the inhomogeneous case when we fix matrix theta and consider different vectors eta. So in fixed matrix or twisted case, we want to see if there is any analog of the statement for all vectors, some analog of Dirichlet theorem. And it turns out that there is one, but this statement, because we are fixing some theta, pretty naturally will depend on the matrix theta itself. So it's not the same for different matrix theta that we fix. After we fix matrix theta, it matters which matrix it is in order to make statements about the sets of vectors. And at this point, before stating the actual results, I want to, in maximal generality, say a few words about the technique, the major technique that we will be using, which is the classical transference principle. Transference principle goes back to Hinchen, who used it mostly in a homogeneous case. Then Jarnik used similar ideas for inhomogeneous approximations and got a lot of results. Then it became classical. It's strengthened in Castle's book. It's studied extensively. There are a lot of new works about this as well. And what the principle says in general is that the asymptotic approximation of the pair are related to uniform approximation of the transposed matrix. And vice versa, uniform approximations of the pair are related to asymptotic approximation of the transposed matrix theta. So we...
Excuse me, but what is the quantification on eta? If you know something about theta, then you know something about all etas or most etas?
Yeah, it depends on what you're asking about, exactly. So that's why I didn't specify. Okay. It depends on which conditions on theta you know. Sometimes you know something for all eta, sometimes you know something about the measures of the set etas. In general, there is some arithmetic relation, and maybe you can get something else from this. Of course, you can also say something about Hausdorff dimensions of eta, and so on using this principle. But basically, this is just a connection in which eta, of course, also plays a role. But in particular, it's possible to to deduce statements for all or for almost all vectors 8. And I will show the example of a proof. I hope I will have enough time for that. I think I will show on some example how this relation works. So what I did not talk about yet is what these functions g and f are and what they are here for. So it turns out more specifically that if we relate functions f and g like they are related here, then transference principle actually allows us to say something of this kind. Suppose that we know the relation of matrix theta transposed to the function f, by which I mean we know if it's f approximable, we know if it's not f approximable, or maybe we know it is f uniform or not f uniform, but we know some information about approximation with this particular function f. Then what the transference principle gives is the approximation for pairs, again, some information depending on what exactly we know, with this function g related to f. So from now on, one more convention that will hold almost for the rest of the talk, except some particular cases where I will say that it does not, is this relation between f and g. If I say g, it means that, and I mentioned also f in text, in formulation of some theorem, it means that f is related to g as it is shown here. And it's also some sort of convolution. Okay, so finally some new results. Some new results, but first result is not really new. First result is mostly due to Jarnik. I called it Jarnik plus because Jarnik did not formulate it in this form. Jarnik had it for functions with several restrictions, and Jarnik also did not have the explicit constant. But basically, it is easy to see that just applying Jarnik's methods, Jarnik's transference, you immediately get this result. So this result is, you can say, reimagined old Jarnik's result. And this result, yeah, sorry, someone wants to ask something. Okay, so this result can be treated as an analog of Dirichlet theorem for this twisted or fixed matrix setup. Particularly, if we know that matrix theta transposed is not f approximable with some f, and g and f are related, as I showed on the previous slide, we know that all the pairs with a fixed matrix theta are Dirichlet or uniformly approximable with almost this matrix, this function g. So by g circle with some constant, I mean composition of this function with a constant function with multiplication by a constant, and many of the results that I will be stating on the next slides will look like this. So I'm saying something not about set of the function g, but set of the function g, which is modified by multiplication by a constant or taking a composition of this function with a constant. And this is the error that we get from these methods. So I will probably make a couple of comments. First comment is that I will, these constants are just there, but I will not talk about them. There are some constant. All of these constant, I do not show the explicit values here, but all of them can be computed. And all of the statements will be formulated up to these constants. So I will not pay much attention to it, maybe studying of how optimal these constants are and how might they can be improved is some other interesting discussion, but today I will not talk about that. Part of it is written in the paper, part of it is just a note. And another comment is that in most of the cases, all our theorems are formulated for functions g without restrictions, but in most of the cases, we want to apply them to some specific functions. There can be powers of t, there can be t to the power something, log t to the power something, or functions of this kind. And for most of the natural functions, again, formally satisfying some technical condition, composition with a constant can be treated as just multiplication by a constant. They are interchangeable, of course, if we change constant a little bit. So I will refer to as up to a constant, and in most cases it just means a multiplicative constant. For some weirdly behaving functions, it can matter that it's not a multiplicative constant, but a constant inside the function. But again, this is the subject of another discussion. So up to some constant, Jarnik has established the analog of Dirichlet theorem for the twisted setup. After fixing the matrix, we know how all the pairs with this matrix are approximate. Probably to make it more clear that it's really an analog of Dirichlet theorem, I need to specify which functions f, well, it's clear which functions f we can take on the functions that theta transpose is not f approximable, but which functions give us the best result. So I'm also not talking about this here, but you can construct, if you have a matrix theta transposed, you can construct in a way the best function that this matrix is approximable by, or the worst function that this matrix is not approximable by, which means, well, in particular, it means that if you multiply it by any constant smaller than 1, this matrix stops being approximable with this function, but not only that. And this is so-called irrationality measure function of this matrix. What you can do is you can basically apply the theorem to f being irrationality measure function of this matrix theta transposed, and then you will get the best possible result for what G is. So if G is a function that's built under the relation we've seen before, using this function f taken as irrationality measure function, we will get the best possible result up to a constant, which will be a Dirichlet theorem. Now, finally, talking about actually new results. So the next question that I asked after we had the classical Dirichlet theorem is, how much can it be improved? How small is the set of matrices where we can improve Dirichlet theorem? And in this case, we can ask the same question: how big is the set of shift vectors where we can improve Jarnik theorem? And it turns out that this set also has measure 0. The only difference is that instead of taking any epsilon smaller than 1, we take constant epsilon which is small enough, where small enough is explicitly stated. Bound, but it's not 1. So up to a constant, the combination of these two theorems gives us the first 0-1 law to discuss today. This is the 0-1 law for uniform twisted approximation. And it shows the precise conditions of when this set of G Dirichlet shift vectors will have full measure and even will be everything, versus, well, it will have measure 0. And because function G is the same in both cases, because, as I said, if we take a rationality measure function, it will be the same. We actually have a gap of just by a constant between measure 0 and full measure. Finally, the last thing I wanted to say on this slide is comment on what's written down here in blue. This theorem does not just work for all the vectors eta, but it works for the case when we consider vectors eta belonging to some affine subspace of Rn. Suppose that we fix some affine subspace of intermediate dimension in Rn. We are living inside this subspace, and we want to consider the set of such etas from this subspace that are Dirichlet with a fixed matrix and fixed function G. It turns out that the same result works for this restriction, for the measure restricted on this subspace as well.
But can you explain, if you have a set of Lebesgue measure 0, then intersection with almost every subspace has measure 0 just by Fubini. So what exactly?
Well, okay, yeah. This formulation is not very precise. So we first of all we talk about, well, there are right.
You have some constructive way of...
There is, right. First of all, there is some constructive way to say which subspaces work and which do not work. I will probably not have time to comment on this constructive way, but it's actually, we can transfer our methods to some subspaces. We cannot transfer our method to some other subspaces. And the other thing that I did not write down here, but I should, is that it's not just almost every subspace. We have a stronger statement that the set of exceptional subspaces, the subspaces for which it does not work, does not just have zero Lebesgue measure, it also has less than maximal Hausdorff dimension. In fact, we can say exactly what this Hausdorff dimension of exceptional subspaces is. So in some sets, you're right that it can be what's written on the slide here can be done by Fubini theorem, but we can say more. We can say that the exceptional subspaces form a much smaller set than just the set of measure zero, and we also know constructively what this set is. Okay,
yeah.
so
I have one question. You said that this is 0-1 law. So this, does it implies that for fixed approximation function G, if we consider the measure of the Dirichlet improvable the vectors for G, it says that the measure has to be 0 or 1, right? Or not?
Actually, no. I expected this question. Maybe I should have addressed this as well. But the answer is that I don't know. I don't know what happens. So we have this gap up to a constant, and we don't know what happens within this gap. So we know that there is full measure, then we go down just by a constant, and then it's measure zero. Are there intermediate measures in between? I would suspect that no, but I don't have more than just rough intuition to say anything for or against it. It is known, yeah, as you know, it's known for asymptotic approximation.
Yeah.
So in this case, I don't know the answer. For asymptotic approximation, the answer is yes. For uniform approximation, maybe it actually follows from something and also not very hard, but at least as of right now, I don't know. So it is in a way still a 0-1 law, but we have something in between. But we will have a completely unquestionable 0-1 law a little bit later, so to justify the name of the talk.
I see.
So before moving to this mentioned 0-1 law, I want to switch the slide to this one, which is not much different from the previous one. It's just stating the theorems from the previous slide in terms of arbitrary weight functions alpha and beta. So the techniques are the same, not many modifications are needed, and we can prove the same two results, analog of Yarnik theorem for all, and analog of Davenport-Schmidt theorem for small enough epsilon for measure zero, in the setup of abstract weight functions. What is useful to notice here? First of all, in the first formulation, my constants moved to alpha and beta. The only reason for it is that I didn't want, for some reason, to put them inside G and in front of G. You can do it as well, and you will also have function G up to a constant rather than alpha and beta up to a constant. So it's all the same. And when we are considering transference, because in this case, norms on Rn and on Rm, or not real norms on Rn and on Rm are different, we need to also switch between alpha and beta. So as you can see, for theta t, we consider f beta alpha approximable. For theta, we consider g alpha beta approximable. All the rest is the same, it's just a direct generalization of the previous slide. One more specific thing, which I will formulate only in terms of classical approximation without weights. We did not do it for weights, and it was actually needed for something else, so there may be some difficulties with generalizing it for weights, but I don't think that they're too serious. For formulating this statement, I need to define what it means to be G singular. G singularity is a natural, again, generalization of usual singularity, where usual singularity means that you are infinitely directly improvable. No matter how small the constant is that you put in front of your function, you are still directly improvable. Now, G singularity means that no matter how small the constant is that you put in front of your function G, you are still Dirichlet with this new function epsilon G. And what we know as a corollary of the previous slide is that if the transposed matrix is F approximable, then the G singular twisted set has zero measure. Now, a small theorem that we show here is that not only it has a zero measure and therefore its complement has full Lebesgue measure, but also this complement is winning in some sort of games. This is probably not, I'm just mentioning it for more or less for completeness. This is not a very strong statement. Knowing that something is already of full measure, there's no surprise that this set is winning. But of course, one does not imply the other. So we also know that this set is winning, and we will have some application of this statement later, which is probably more interesting than just the general statement. Okay, now we finally are ready to switch from twisted approximation to approximations of pairs, and we are ready to talk about so-called Dirichlet theorem for pairs. Dirichlet theorem for pairs in the so-called inhomogeneous Dirichlet theorem was formulated by Kleinbock and Wadleigh for classical subnorms, and it stated that the set of G Dirichlet pairs, you see we don't have a fixed matrix theta anymore, has zero or full measure depending on convergence properties of this series. If the series diverges, the measure is zero. If the series converges, the measure is full. So this is a nice 0-1 result. Maybe it's a little bit confusing to call it Dirichlet theorem because it's not a result for all, it's just a result for almost all. So I would say that in some sense it's an uniform and homogeneous Khinchin-Groshev theorem. And it's actually more related to Khinchin-Groshev theorem than just its form. What we will prove here is an analog of this statement for arbitrary weight functions. So this is a direct generalization for the set of G Dirichlet pairs with weight functions alpha and beta. And you can easily check that if we take alpha and beta to be the ones that guarantee the usual subnorms, which is beta G equals T to the power 1 over m and alpha I equals T to the power 1 over n, we exactly get the series above. So my goal is to do two things. First of all, I want to prove this new result, which is a generalization of the old result. In particular, this new result implies the same 0-1 law for classical approximations with weights. And second, I will present a new approach to proving this result, which of course, as for a special case, works for the Kleinbock and Wadleigh theorem as well. So they were doing it via dynamics on the space of grids, space of inhomogeneous lattices, and there was some shrink and target problem. This problem was reduced to this shrink and target problem, and then by some dynamical methods, this shrink and target problem implied this convergence or divergence relation. We will do it differently. We will use the theorem that we just saw, almost 0-1 law for twisted uniform approximation. And then we will apply this law. This law basically says something about the sections of this set D. We will apply this law to Khinchin-Groshev, classical Khinchin-Groshev theorem. And we will see how their combination implies this result. And to save some time and not to make the notation too long, I will only talk about this proof for the classical case. So I will only prove the already known theorem by a new method. But this new method, this transference method, can as well be applied to the second theorem, to the more general theorem. It just becomes more technical. You need to prove some lemmas that some convergence here is the same as convergence here. So it's rather technical and not too short, but there is nothing under it. It's just technicality. Okay, so what I already have mentioned, and what probably seems in its spirit similar to inhomogeneous Dirichlet theorem, is the well-known Hinch-Grotov theorem. Hinch-Grotov theorem is a classical 0-1 law for homogeneous asymptotic approximation. And it says that the set of F approximable, not F uniform, but F approximable matrices has 0 of full measure depending on just convergence or divergence of this simple series of Fk. The analog of the theorem is also known for the general weighted functions. And this is actually the first time where quasi-multiplicativity plays a role. If we assume that our alpha I and beta j are quasi-multiplicative, then we can prove the following generalization of the 0-1 law. It's done by Kleinbock and Wadleigh just a couple of years ago. So this is a nice and direct generalization of Hinch-Grotov theorem. For them, it's done in a little bit more general setup than this. They have independent functions f sub I instead of beta j of the same f. But quasi-multiplicativity condition is still required for their proof as well. So this is where it comes from. Now, our goal is to use our twisted uniform approximation theorems to prove that Hinch-Grotov theorem and inhomogeneous Dirichlet theorem are equivalent. One implies that. What we have to notice for this, the main observation, is basically that these two integrals converge or diverge at the same time, where f and g are related as they are always related. And these integrals corresponds to the series in Hinch-Grotov theorem, and another correspond to the series in inhomogeneous Dirichlet theorem. This relation becomes more complicated. This equivalence becomes less clear with the abstract weighted functions, but it still holds. After we know that this relation holds, we can consider two cases. First of all, suppose that the series from inhomogeneous Dirichlet theorem converges. It means that the series from Hinch-Grotov theorem of just functions f also converges. This implies that almost every matrix theta transposed is not f approximable. If it is not f approximable, then by Jarnik's theorem, the twisted set of G Dirichlet consists of all the vectors in Rn. Of course, here the up to constant thing comes to play, but you can notice that the convergence of the, first of all, you can transfer this constant from G to F and from F to G in both directions as you wanted, and both constants inside the function and multiplicative constant do not change the convergence or divergence properties, so it really doesn't matter for this. So we know that if the series converges, then the sections with a fixed matrix have full measure and even are the whole Rn for almost every theta. Then it remains just to apply the aforementioned Fubini theorem to say that this holds, the full measure holds for the whole set of pairs. The other way around, we do the same. Suppose that the matrix, the series diverges. Then by Hinch-Grotov theorem, almost every transposed matrix is f approximable. If it is f approximable, we apply the inhomogeneous Davenport-Schmidt theorem, the twisted Davenport-Schmidt theorem, and show that in almost all sections, the measure of this slice will be equal to 0. If the measure of this slice is equal to 0, then again, by Fubini, the measure of pairs is also 0. Therefore, almost no pairs are G-Dirichlet. And again, we can ignore up to a constant thing because it does not change the convergence or divergence properties. This completes the proof of this 0-1 law. And what I really wanted to show here, it's a little bit more technical for weighted functions, but the idea that we use is the same. There is nothing else here. And this provides a modular Hitchin-Groshev, which we, of course, have to separately prove, but I guess this is already a classical statement, at least without weights. And modular our twisted theorems. This inhomogeneous Dirichlet theorem proof becomes very short and very clear. Okay, so this is probably the main result that I wanted to address today in some sense, but we have many more. I will try to, I think I'm running out of time, but I will show at least some more results and maybe some twisted proofs. Let's see how it goes. So I want to shortly comment on another matter, which is not about Lebesgue measures anymore. I wanted to ask a question: what happens when the measure of the set is 0? First of all, a natural question is how big this set when the measure is 0 from the point of view of Hausdorff dimension. This is also done without weights in the classical setup by Tae Hong and Woo Yeon in their paper. But let's ask an even more ambitious question in some sense. What happens if even Hausdorff dimension will be 0? It's also regulated by convergence and divergence of some series. So imagine that the Hausdorff dimension is also 0. Can we at least guarantee that this set of Dirichlet is non-empty if the function g is decreasing very, very fast? And can we say something about this for the general weight function? So it turns out that the answer, non-surprisingly, but still, will always be yes, the set is non-empty. Moreover, this set will always be uncountable and dense, which is analogous to famous Yarnik theorem in homogeneous Diophantine approximation. This is some teaser for some work in progress, and a special case of some new theorem that we are working on right now. But the answer is here, and actually you can prove more of this. Okay, now I will shortly talk about some applications. So all this talk was so far about abstract functions f and g, without any restrictions or with some minor restrictions, which is interesting, but it's probably not what most of the people usually do. Mostly people are interested in some fixed function and working with some sets, like the classical set of badly approximable numbers, for example, where there is no abstract function, the function is always fixed. I will probably skip the introduction of badly approximable numbers. It will not be too important for us. What property this set has measure 0, the set is winning. This is all rather well known, and the idea is that it's the set of the matrices that are asymptotically cannot be approximated better up to a multiplicative constant than guaranteed for all matrices by Dirichlet theory. We can define badly approximable matrices for general weight functions as well. That's what I mentioned the generalized Dirichlet theorem for. This set also has some nice properties. For example, it also has measure 0, as follows from generalized Hitchin-Groshev. It also corresponds to bounded trajectories on the space of lattices, but I'm not talking about this right now. It also holds a lot of nice properties. Yeah, for example, one of the properties that the transposed matrix to badly approximable matrix is still badly approximable. Now we want to present one criterion of bad approximability in terms of these generalized badly approximable numbers. And this criterion is actually stronger than just criterion. It says something about the measures. So this is a criterion in terms of uniform and homogeneous approximation. If our matrix is badly approximable, then up to some constant, every pair is Dirichlet with the correct function. The correct function is the same function as holds for Dirichlet theorem for the arbitrary weight set. If you are not used to these abstract functions, you can think of the classical setup, and this G alpha beta just becomes our function f1, which is the function 1 over t. So almost any pair is Dirichlet with this function G, with this function in particular f1. And if our matrix is not badly approximable, then not only the previous statement does not hold, but we also know that every such pair, the set of such pairs that are f1 Dirichlet or G alpha beta Dirichlet with some constant k has Lebesgue measure 0. So it's not just that this set is everything and the other set, in the other case, the set is not everything, but it's actually either everything or measure 0. I need to notice that this follows directly, at least in non-weighted case, from our Davenport-Schmidt theorem that's in our paper with Nikolai. This can be proved for the weight functions using the weight function version of Davenport-Schmidt and Dirichlet theorem. And this criterion is also stated and used in a recent paper by David Simmons, Keith Merrill, David Lambert, and Lior Fishman. They use similar statements about badly approximable numbers and about very well approximable numbers for this Waldschmidt's conjecture. So this actually, I'm saying all this because just to state that this actually has some applications for problems outside of just inhomogeneous Diophantine approximation. Here is actually a cleaner formulation. A cleaner formulation that shows this criterion. And in the non-weighted case, we can say even more. We can also say that the complement of this set of measure 0 does not just have full measure, but it's also hyperplane absolute winning set, which follows from our hyperplane absolute winning theorem that I formulated. Another thing that we have is a similar criterion for very well approximability. In this case, we only have it for classical weights. And I will probably not really stop here. I will just mention that I mentioned this criterion because it's also used in this paper about Waldschmidt's conjecture. And we do it, we generalize it for the setup with weights. Okay, Dmitry, please tell me if I have to stop because I don't have any time left.
Yeah, well, we need to finish maybe in 5 or 10 minutes, probably, because people will have other assignments. But why don't we have a round of applause right now? And then maybe virtual or real. This was nice.
Oh.
So if okay, and then maybe some people have questions. Any questions, comments?
So my plan was just shortly to explain my idea. Yeah. So I have some more slides here. I can speak about them now. I can answer questions first. I don't have to speak about them at all. That's up to you. What do you think is better?
I can ask a quick question. What is the proof of twisted Davenport-Schmidt's theorem?
Okay, yeah, thank you. That's a very interesting question, and magically I'm very well prepared for answering this precise question. So I want to state the proof of what I call the twisted Davenport-Schmidt theorem and show actually how our transference techniques work in the first non-trivial case, but this is still a rather straightforward and clean proof. So a reminder is that we want to prove the following fact. If a matrix theta transposed is approximable with the function f and with weights beta and alpha, then the measure of the set of G-Dirichlet shift vectors up to some constant epsilon will be 0. So I start with looking at the so-called, well, this is not exactly what we call best approximation vectors. So y nu is just a sequence of vectors which gives us this rate of approximation. Rate of approximation symptotically with the function. So let's fix the sequence of these vectors, and later on we will switch from this sequence of vectors to a more rare subsequence, for which this condition 3 also holds. If it holds for all the vectors from sequence, then it holds for the more rare subsequence. We also have this statement that follows from quasi-multiplicativity, and basically what it is that if we, so roughly speaking, if we take alpha of t multiplied by alpha of 1 over t, by quasi-multiplicativity we get 1. If the product of arguments is small enough, then the product of functions also becomes small enough. That's what we use by quasi-multiplicativity. And now we want to show how the theorem can actually be proved. We can do this in 2 steps. First step is we are taking this set of shift vectors eta which provide us Dirichlet pairs and show how it is contained in a certain limit set of sets which are A, explicitly described in terms of our sequence y nu, and B is actually has a very nice and clear structure. Second part, we want to estimate the measure of this set. So we want to have some upper bound and prove that for parameter epsilon small enough, this measure will be equal to 0. And the set that we are talking about is actually this set omega lim set of omega nu, where omega nu is the set where the, so you see the definition here, but what it is we are looking at the hyperplanes eta multiplied by scalar product with y nu is equal to 0, and we are considering thin neighborhoods of these all hyperplanes. So it consists of, let's probably for simplicity switch to 2-dimensional case. It consists of many regularly spaced thin stripes. So we want to prove that as a part 1, as a step 1, as the set of Dirichlet shift vectors is contained in a lim-inf set of these sets. Well, to do this, we actually need a transference. We check some, we choose some parameters here, which I'll probably skip for now. And what we base our observations on is this famous relation. This relation can be directly noticed. And there are some easy corollaries in terms of norms here, as well as the regular norms. We can have similar ones in terms of weight functions alpha and beta. So we use the inequalities following from, in one case, approximability, because our assumption is that theta transposed is f approximable. In the second line, from the pair being Dirichlet, to have these 2 bounds by alphas and betas. These 2 bounds give bounds for the terms on the right-hand side of this transference relation, and all of it combined together with the observation that I've showed before, that we can make these products as small as we want. In particular, we can make them smaller than delta. This all results in this inequality, that if eta is a shift that provides us a G-Dirichlet pair, then this inequality holds. Therefore, we immediately prove the whole thing. We show that the inequality for the G-Dirichlet property should hold starting from some point, which basically means that is contained in a lim-inf set. And part 2, we need to actually estimate the measure of lim-inf set consisting of these stripes. And the trick that we're doing here is the rest of the proof I will just show on the picture. So this is how the set omega nu looks like. As I said, they're evenly spaced strips, and they are as close to each other as 1 over length of the vector y nu. Now imagine that we take the intersection of this set of stripes with the next, the one numbered nu plus 1. What we want to notice is that these two sets are, no matter what the angles are almost independent metrically, which means that the measure of their intersection is close to the product of their measures. Of course, that may not hold if y nu and y nu plus 1 are close to each other. You can draw the picture when one of them is the other shifted or something like this. But once we make nu plus first term smaller and smaller, these stripes become comparably to the previous stage thinner and thinner. And it's rather easy to show that we have independence.
Looks like we got the main idea.
Yeah, and basically independence covers it.
Yeah, it will be great to watch these cartoons for 5 or 10 more minutes, but unfortunately we are out of time.
Yeah, sure.
So
Now it's definitely.
are there any quick questions, comments, objections to main results? Well, if not, let's thank Vasiliy again. This was a very nice presentation.